Welcome everyone to this fifth ISAMP web colloquium. And it is a pleasure to invite Professor Gopal Dixit today, who is from IIT Bombay. So Professor Dixit did his PhD from IIT Kharagpur, and after that he moved to Center for Free Electron Laser Science in Hamburg, Germany, and subsequently to in Max Born Institute in Berlin, right, where so he spent around 8 years as guest scientist in Germany, and then in 2015 he joined IIT Bombay as faculty in physics department. Right? He has received several prestigious fellowships like the DART Fellowship, the Marie Curie Fellowship, and the Ramanujan Early Career Research Award. Right, and currently he is the associate professor in the physics department of IIT Bombay, as well as I think a visiting faculty in Max Born Institute, Berlin. Right? So with this, I would like to request Professor Dixit to give his talk.
Thank you very much, Professor Aditya, for invitation and your kind introduction. So let me share the screen and narrate the interesting story that we are recently doing in our group in Bombay. So I hope you could see my screen. So what I'm going to tell today is coherent control of value tronics in graphene, which is a new avenue for quantum technology when it comes to the graphene. As I assume that it is kind of little bit new topic for some of the audience, so I will introduce what I mean by the valleytronics, how it is related to the graphene, then what I mean by the coherent control, and then how it can be useful for quantum technology. So before I introduce Valley, let's revisit what we know in a very simple term. So we know that electrons have a charge as a degree of freedom. And this charge of the electron is used, for example, making the transistors, which form the ingredient of this Intel chip. So how this works? So we know that we make a very simple transistor, which is kind of a control knob, which allows you to flow the charge or don't flow the charge if you put the switch on, switch off mode. So this allows you whether the information or data is on, or the flow of data is on, or the flow of the data is off. If we start putting the transistors in a appropriate way, then you form different kind of logic gates. Okay, and if you put different kind of logic gates, you form the basic modules, and these are the basic modules which perform different kind of basic operations in your computer. So if you take these different modules and put together, so you see you have a different combinations of different logic gates, and these logic gates are going to give different kind of arithmetic basic operations in computer. So as we agreed that the flow of the charges, which is a degree of freedom related to the electron, is an important ingredient for your transistor, and this forms the circuit chip. So not only the charges are utilized to make different kind of ICs, but they are also used to form, let's say, the charge coupled devices. So one of the common example that you have came across is the CCD camera, but even for the experimentalists, this CCD is used to record different kind of signals. So this is some basic applications of, you could say, the charges. Okay. Now electron has another degree of freedom, which is spin. So if you say what are the use or applications of the spin, so let's say you form different kind of layered structures, and these layered structures are used to form different kind of spin walls, or if you put in a different arrangement of different kind of magnetic materials, they form these small memory chips. Okay, so we know that electrons have a charge as well as the spin degrees of freedom, Now, what electrons have in 2D materials or any solids, let's say valley degrees of freedom. This is an additional degree of freedom of the electron. So let's say here I have taken this two-dimensional material, which is kind of hexagonal pattern arranged in this following fashion. And if you look, so this is your real space structure of your material. And if you go to the momentum space and this translate this hexagonal structure from real space to the momentum space. So this is your gamma, which is a kind of center. And if you look these points at hexagons, these are what we call as a high symmetry points of your 2D material. And if you look the energy structure of this material, see this y-axis is your energy and x-axis is your momentum. So at these high symmetry points, K prime and K, you see that this is your valence band maxima, and this is your conduction band minima, and this is your Fermi energy, if you call it. So you could see that at K prime and at K, you have a valence band maxima or conduction band minima. So these 2 points are, first of all, energy degenerate because these are energetically equivalent, and they have the maxima here or the minima here. So that's are called as a valleys. So these are the valleys in the materials. That's what we call as a new degrees of freedom of electron in solid system, and these valleys. So as I said, that states K and K prime are energy degenerate, but they are opposite in momentum. Now the task is that how we are going to distinguish these two values which are energetically same, how we are going to break this degeneration. Can we differentiate it? Okay. So now let me take a very simplified picture instead of taking the complete energy diagram of this particular material, and say that, let's say these are the 2 points, K and K prime value. And by some means, I will come to this point, how we can do it. By some means, if we can excite the electron at K value, not to the K prime values, or other way around, if we can excite the electron at K prime value, not at the K value, okay, then we can treat this system as, let's say, 0, or this state we can call as a 0, and this state we can call as 1. And now we are almost at the same footing, what we call as a spin up or spin down, or spin is in state 0 or spin is state in 1, or you can say that the flow of charge is on or off, what I have introduced in the beginning by taking the example of the transistor. Okay, so these two isoenergetic values can be also treated as 0 or 1 state. Okay, and not only these can be only in 0 or 1, but they can be in linear superposition of the two values. So here is the block pair representation. So you see this is your kind of vertical axis or G axis. Okay, so you are either at K or K prime value, but by some means, if you can create a superposition state, then you are into much better position. Unlike the spin or the charges, here you have the opportunities to create a linear superposition so that your two values can be coherently populated, or they can be also coherently coupled with each other. Okay, so now what the meaning of the value tronics? So the literal meaning of the value tronics is that we want to do the electronics, but not with the charge or spin, but with the values, because values gives the opportunity not only going to be the 0 or 1 state, but in the linear superposition of these two states. So when somebody calls, we want to make a device based on the valuetronics, it requires at least the 4 minimum steps. The first, we want to distinguish the values, so that we want to distinguish K and K prime are two independent things. We want to achieve value polarization. So we want to control when we want to only populate K value or K prime value. Once we have populated, we want to also detect that the K value is populated or K prime value is populated. And now we want to control over the value properties. Once we have ticked all the 4 important ingredients, then we can say that our material or our system is ready for the valuetronics devices. And this is the talk where I'm going to convince you that graphene possesses all the properties. But before that, let me pose a challenge why it is a new thing that we are going to discuss and why there was a problem till date. Okay, and just for experts that K and K prime values are related by the time reversal symmetry. Okay, so what are the possible devices that can be met by using value tronics? So of course, as I said, that quantum computing, so we can form the qubits based on the K and K prime because it possesses all the important quality that is needed to form a qubit. It can also go to the classical computing, unlike 0 or 1 or on and off of the transistor. So we can have a value tronic switches, and they are going to be the low power transistor, and they can also be combined with the spintronics. I will come to a point of the spintronics, and they can be also used to form, let's say, photonic applications, for example, circularly polarized light emitters, or the polarization sensitive detectors, or optical isolators. Okay, so let me go one by one. So when I say value polarization or value asymmetry between the two values, what I mean that we want to achieve either one value is preferred for any kind of excitation or operation over the other values, and this can be either this can be obtained either by breaking the inversion symmetry or breaking the time reversal symmetry. So, for example, this material which I have showed you a few slides back, you can see that if you look in this one particular hexagon, this does not obey the inversion symmetry because these and these, the what you say, the green or yellow, these are the two different atoms. Okay, so what these could be two different things. So one atoms can be so these are generally called as a transition metal dichalcogenide. So M can be molybdenum or tungsten, and X can be S sulfur, selenium, tellurium. And if you go into the classification of these material, so you see that WTE2 is semi-metal, so it does not have any band gap, and MOS2, MOSE2, and these materials are semiconductors with appropriate band gap, and MOTE2 is the relatively band gap. I will come to in the next slide why the band gap is an important concept. Okay, and the band gap arises because this system is composed of two different kind of atoms. Okay? So it breaks the inversion symmetry.
Question, Gopal?
Yes?
Yeah. So,
Yes? Can you hear me?
I can hear you.
Yeah, yeah.
So, why is it? I mean, how this Valitronics becomes a low power electronics?
I'm coming to a point. This one, I will come to a point.
Okay, thanks.
So let's say you have the two values, and based on detailed selection rule, what people have shown that K value can be selectively controlled, or let's say the electron from the lower level to the upper level can be selectively excited by using, let's say, the sigma minus polarized light, whereas the K prime value can be selectively excited using the sigma plus value. So once you have a finite gap between the upper level and the lower level, then one of the helicity of the light controls one of the value, and the other helicity of the light controls the other value. And you need a band gap to have a resonant excitation between the lower level and the upper level. Now, if you include the spin orbit coupling, so this is your reference level. And now once you have included the spin orbit coupling in these kind of materials, so you see that the lower level has an upper level shift upward and downward with respect to this reference level, and these two levels are differently connected to the conduction band, and then you start kind of spin locking. So that's how this spin related Valitronics devices can be obtained, and these are the detailed selection rules. So if you have any questions, I can discuss at the end of the this talk, but I don't want to go into too much mathematics. So at least one thing is clear, and take let's conclude from this slide that to selectively excite an electron from the lower level to the upper level, you need a band gap. Okay, that is the only concept I'm going to take forward from this slide. Okay, so the values in 2D materials have potential for quantum information processing, and these are all the operations are performed at the room temperature. Now here is a challenge. So maintaining the homogeneity during the sample preparation of MX2 is challenging. Moreover, realizing experiment on these quantum materials without any substrate is not straightforward, because unlike the holy grail of the 2D material, that is graphene, which is based on the Scotch tape technology, the preparation of these MOX2 kind of material or MX2 kind of materials are completely different. And if you want to have a kind of certain size of the 2D material, thick sheet of this material, then you have a potential to have different kind of defects, vacancies, and all these things, and that can create a problem when you want to create a qubit. Okay, so in this all point of view, monolayer graphene is much better, and it's commercially much cheaper in comparison to these materials. But what is the problem with graphene? So let me come to the graphene. So unlike the previous material, graphene is composed of the same kind of atoms. So you see that all the atoms are the same. So now you do not have the breaking up inversion symmetry, but you have the inversion symmetry in this system. And now if you look the band gap, so this is the energy structure with the high symmetry point, and you see that along these two high symmetry points, K and K prime, you do not have any band gap. That's why the graphene is a semi-metal in nature, so you do not have any band gap. So the resonant kind of excitation scheme cannot be applied to the graphene. Okay, so it means that graphene is not suited for any kind of electronics application. That's what the conclusion before our paper came out this year. The people have attempted to break the inversion symmetry, and there are a couple of ways. One way is that you chemically modify this system by doping or substitution, which can open some few millieV to tens of millieV band gap, and getting the appropriate laser of that energy is not suited. The other options are you put this graphene into some kind of substrate, so you have this heterostructure, and because of the lattice mismatch, some band gaps open up. So now you are not working with the graphene, but you are working with the heterostructure, and a lot of properties of the graphene is modified. Okay. So with this zero band gap, and it has zero Berry curvature and its identical dispersion at the bottom of the two valleys, what people have concluded that graphene is not suited for electronics devices, which is a very disappointing conclusion when you look that graphene is much better when it comes to the transport properties, unlike any other equivalent 2D materials. So now how to overcome this problem? So here is the energy contour of your graphene, and these are the K and K prime values. So these are the energy contours. Now the idea is as follows, and it's very simple without going into mathematics. So let's say electron is at K and K prime values, and if you move little bit away from these two values, you see these isotropic circles, which are the energy lines. Now, if by some means you overcome this isotropic region and you reach to this anisotropic region, if you follow my cursor up in my screen, so you see that if I'm at this point, and if I'm at this point, then electron will see different energy environment. And if I by some means I can take this electron here, and equivalently I can take this electron here, then the electron in K and K prime values will see different environment, and then you can create the valley polarization. Okay, how you can do it? So based on some intelligent guess, what we have done, we have taken the combination of the two lights. One light is left-handed circularly polarized, and another light is right-handed circularly polarized light with double the frequency of the fundamental. So if you combine the two circularly polarized light, then the total field looks like this threefold symmetry. Okay, and it doesn't mean if you change the polarization of omega with 2 omega to omega with omega, the total structure of your electric field remains same, And if you now put this total electric field to these two values before this one, and now by controlling the delay between the two lights, omega and 2 omega, you can rotate the this threefold structure the way you want. Okay, so at 90 degree it reverses back. So now this leaf is pointing along forward direction. At 90 degree this leaf will point along the backward direction, and after 180 degree it return back to the original position. Okay, so either you can call as a time delay between the two lights, or you can call as the sub cycle phase between the two lights, which is the equivalent thing. Okay, so now this is the graphene hexagonal structure. Okay, and this threefold at phi is equal to 0 fits exactly with one value. Look at this, and again this contour, but it doesn't fit to the another value, and that is the reason that you are going to create a imbalance between the two values, and you are going to create a polarization between the two values. Now once I change my phi from 0 to 90, now this total electric field of my light fits with the k prime value but not with the k values, and then in this way I can control the excitations in one of the values over the other values. Okay, so what are the results? Here are the results. So here is my let's say value asymmetry parameter, which is the population difference between the two values normalized by the mean, and this is my subcycle phase phi, which is given here, and this is the intensity of my light, goes from 0.5 to 3 in units of 10 to the power 11 watt per centimeter square, and this intensity is below the damage threshold, so it does not create any permanent damage to your graphene single layer. And you see that your value asymmetry parameter, when phi is 0, when it fits to the one value, you can create a value polarization up to almost like a 40%. And as you go to the 90, as I suggested you that it fits to other value, then you create a value polarization to other value of the same strength, and your value polarization is modulating after 180 degree. Okay, so what it means that by careful choosing the value of the phi, you can create the value polarization between plus 40 degree to minus 40 degree between the two values, whatever you want. The other thing is that this green line shows another interesting aspect, that if the intensity of laser is weak, then you don't see any value polarization. The reason is simple, because if the strength of your electric field is weak, then the electron which is moving in this one and in this one sees only the isotropic region. So you need to put a more force so that the electron starts seeing the anisotropic regions of the two values. So you need to have a critical value of your electric field. After that, your electron starts seeing the value polarization, and this green curve is for phi is equal to 0. Okay, and these red dotted lines are for 3 into 10 to the power 11. So indeed, you are able to control the value polarization. Now, okay, you have created the value polarization and you have created the way you wanted, but how to measure it? That is the next thing. So what we have done it till now? We have now distinguished the two values. We have created the value polarization between the two values. Now the third step is that how to measure the value polarization. And to measure the value polarization, so this work is done by the Mridul, who just completed the PhD in my group. And now here you can see that how the value polarization scales with the wavelength of your laser, as well as the strength of your electric field. So you can see that by going longer and longer wavelength, or by making intense and intense laser, you can create a value polarization up to 60% in graphene. Okay, and here is the same data, but here it is shown in a scattered way. So it shows that up to almost like 0.3 atomic unit of your vector potential of your light, you don't see any value polarization, and after that you start seeing the linear increase in the value polarization. And the reason to have a linear increase in the value polarization is simple, because if you look your momentum of your electron, so if there is no light, your momentum of the electron is p, And once you switch on the light, your momentum of the electron P translate from P to P plus AT, that is the basic quantum mechanics that you have learned, or even the classical mechanics. So then your change in the momentum or change in the velocity depends linearly with the vector potential, and that's how you are seeing the linear increase in the valley asymmetry parameter. Okay, now let's ask the following question. Is there any other combinations of your tailored light by which you can control the valley polarization? So what we have done, instead of taking omega 2 omega, we have taken omega 3 omega combinations. And in omega 3 omega, the total electric field has 4-fold symmetry. This 4-fold symmetry does not fit to any of the valley, and that's why we do not see any significant valley polarization. This is a very weak valley polarization, which is very, very small. So indeed, you need to be careful when you are choosing what kind of valley polarization you want. Then you need to careful tailor your light, what light you want. Okay. So now, how to measure?
Gopal, may I ask a question?
Yes.
Yeah. So for the third harmonic, why at all there is any variation in the polarization? Because by third harmonic, you will not be breaking the inversion symmetry at all, right?
Yes, we don't break. That's why it's not there, right? So when we have this omega 3 omega, and when we fit into this energy contour, let me go to this one, it does not break the inversion symmetry between the two valleys. That's why we do not have any valley polarization. The only valley polarization comes because of a small, you could say, numerical issue or a small transverse motion of the electron away from the valleys. That's it. Is this the answer? Is this the question that you are looking at?
Yeah, so this is basically within the error bar of your numerical calculation, is it?
Yes, yes, you could say it, yes.
Okay, fine.
So now to probing the valley polarization, what we have a method chosen is high harmonic generation. So before I go and show the result, let me discuss what is the high harmonic generation in solid. So let's say again, you have a conduction band and you have a valence band. You shine intense light. What will happen? Some of the electrons from the valence band will be promoted to the conduction band. So you create a hole here and you create an electron, and your laser is on. So what the laser will do, it will drive the electron away from this one because it's oscillating back and forth, and the hole will also oscillate in this respective band. So what kind of motion you have? So you have an intra-band current because your charge carriers are moving in their respective bands, and because your light is changing its direction back and forth, up and down in a sinusoidal way. So there are also probability that this electron can recombine to the hole, and when there is a recombination, it can emit a radiation. So the total current has a two-part, interband and intraband, and these currents are emitting a radiation. So if you look the typical spectra of this process is something like that. So here is your intensity in arbitrary unit, and here is your photon energy. And this spectra corresponds to this realistic material. So these are your two valence band shown in the green. The minimum energy gap between the valence band and conduction band is given in Eg. So when your energy up here is shown in this color. So these harmonics are, you can see that the next peak, all peaks are gradually decreasing. And this is a signature that what you have seen probably in the perturbation theory, that all the higher order signal is weaker to the previous order signal. So definitely this is a signature of your perturbative treatment. But once you cross to this band gap regime and your electrons are populated to this one, then you start seeing the interband and intraband, and all the harmonics are of equal intensity, and then your perturbation theory is not anymore applicable. And once it reaches to this boundary, now electron can climb to this level, and these are different energy cutoffs which are scalable with the different energy parameters that your solid mimic. Okay, so now this is the total harmonic spectra of our graphene driven by omega 2 omega bicircular, and you see that the first harmonic is have the polarization to the left circular, the second harmonic side, the right circular, and because of the threefold symmetry, and there's a detailed selection rule, all your 3 enharmonics are absent. So you do not have third harmonic, sixth harmonics, ninth harmonics, and so on and so forth. Okay. Now, if you see how your particular harmonics are sensitive to the subcycle phase, so you see modulations of your fourth harmonics, of your fifth harmonic, sixth is absent. You have a modulation, and if you can resolve into the valley point of view, then you can see that at that particular point, either the K valley or the K prime valley is contributing to the total harmonics. That is the one important consequence, that once you measure the total harmonic spectra, you know that at what value of phi, which harmonics is contributing much more. Okay, so definitely the valley polarized, high harmonics are valley polarized. What we have suggested that along with the omega 2 omega, we can send a 3 omega as a probe, which will be all optical probe of the valley polarization without any background, without any reference. And once you have broken the inversion symmetry using omega 2 omega, then you will start seeing the 6 harmonics peak, which was absent in the case of omega 2 omega. The 6th harmonic peak is coming because of your valley polarization. And by tuning the phase of your subcycle, you can say that either one is in phase, one is out of the phase. And in this way, so this is your harmonic 6 in different time. And in this way, you can probe it. So indeed, I hope that I have convinced you that not only you can control the valley polarization between the two valleys the way you want, the amount you want, but you can also probe using the third omega, 3 omega probe pulse using high harmonic generation. Now let me come to another way to probe and create the valley polarization. And this is a recent result which is under review. So again, this is your band structure. You have K and K prime valley. Now by some means, if I have a light which is along K prime valley, and by some means, if I can create imbalance between the two, then I can create a valley polarization. So what I have done, instead of a very long pulse, in the previous slide, you have hopefully seen that the pulse duration is really hundreds of femtosecond. Instead of that, what I can do, I can take a very short pulse and I can tune the subcycle. I can tune the carrier envelope phase. What is the meaning of the carrier envelope phase? So these are the oscillations of your light, and the blue is shown in the envelope. So if the peak of the two, the subcycle phase and the envelope is matching, then you have CP0. And if you have offset, then you have a pi by 2. If it reverses, you have a pi value of the envelope phase. And at 2 pi, it returns back. Okay, at pi, it reverses back. Okay, so you need a pulse which is not symmetric in time. Okay, so you see this is my single cycle pulse, which is around 25 femtosecond, and you see the vector potential. This is the vector potential. So upward and downward are not symmetric. So this is my 0. So upward is little bit and downward is more. And that's what it creates the valley polarization. This is a single cycle pulse. And here is the result. So you can see that in one cycle, you create a valley polarization and it reaches more than 50%. And as we tune the CEP carrier envelope phase, and I showed you that at 90, it reverses, and at 180, it goes opposite way. So it goes to another valley, and then at 360, it comes back to the same valley. Now, as you increase the number of cycles of your single cycle pulse, then your upward and downward components are kind of equivalent, and then you start losing this asymmetry. And that is also reflected that you are not anymore able to create asymmetry in the valley polarization. So this is your 3 cycle pulse, and you see the data of the 3 cycle pulse, which is in the gray color. You see nothing. These are all integration numerical noise that is coming out. And when you have a 2 cycle already reduced by almost factor 2. So you are above 0.5, and here you are almost 0.25. Okay. So there are 2 ways that you can control the valley polarization. One is omega 2 omega bicircular field. And this is the new way that we can come up with a single cycle CP controlled pulse, which is another way to control it. So let me conclude that I hope that I have convinced you that the Taylor fields can be used to control valley polarization. And moreover, this valley polarization can be read out in background free all optical way using high harmonic generation. Now, where is the future? Okay, note down, all these operations are at room temperature. So what we are thinking that we are going to create a qubit at the room temperature in graphene, in realistic material. Okay, and in future, I'm not saying that in coming few years or so, what people are predicting or what people are going, that this is the future that you can have, let's say, a quantum computer at ambient temperature instead of at minus 240 Fahrenheit or so. Okay. Now, what is another take-home message from these work? So we know that all the laptop, all the electronic devices are based on your semiconductor chips, and the operational speed of all the semiconductor in various electronic and optoelectronic devices are limited to several gigahertz. And to convert the gigahertz is 1 billion oscillations per second. And this is the upper limit of your operational speed of computing. And from last 10 years, even last 15 years, the clock speed of your laptop has not gone beyond gigahertz. It has changed some number from 1.5 to 1.6 to 1.7 to 1.8, but there's no order of magnitude improvement, not even going from single digit to the double digit. Okay. Now, what is the alternate way to change it? Instead of using this conventional CMOS technology, what you are going to use, the light waves perform several hundred trillions oscillations per second. Instead of billion, lights are oscillating in 1 second trillion, several trillion times. So it is natural to see that these light oscillations can drive the electronic motions. And unlike these conventional techniques, light not only trigger the motion, but it also controls the motion of the electron on natural time scale. That's what I have shown you, that the valley polarization can be controlled by choosing the properties of your light, for example, polarization, R intensity, or carrier envelope phase. Okay. So what it means that by applying the light and the valleytronics, there is a potential to increase the operational speed of devices. That is the field that people are working, and we are also working on petahertz electronics, which will improve the computing by orders of magnitude and open the avenue for petahertz electronics. Now, coming back to the question of, let's say, non-heating or how the heat-reduced valleytronics can be done. So you see the operations that we are creating are the polarization results I have shown. These are after switching up the laser. So the population remains there for several hundreds of femtosecond after switching up the laser. So there is no source. There is no source of heat that is causing it. Okay. And these are quick flashes of light. So there is no sources of heat. So let me acknowledge first part of the work is done in the collaboration with Misha Ivanov from MBI and the postdoc Alvaro Galan. Recently our work has got into this Association of Computing Machinery, IEEE. So if you want to see almost a 1 hour interview, you just log in into ACM or IEEE Thames, and you can see this one. And this work is also going to appear in the Forbes magazine published in USA. With that, thank you very much for your kind attention. This is the group. And let me again thank you very much for Mridul to pulling out this very interesting project that was considered as impossible to see the valley polarization or valleytronics in pristine graphene. Thank you very much.
Okay. So thank you, Professor Dixit. And now the talk is open for a few questions from audience. So if you have any question, you can either like ask directly, or you can also type in the chat box, and then I can take it.
So can I ask? I mean, can I start asking so that others?
Yeah, sure.
Yeah.
Sure.
Hey Gopal, I actually was wondering. See, you have this the last result that you are showing about the CP dependence and the asymmetry in the field within one envelope that is causing this polarization or valley polarization much more for the single cycle rather than multiple cycles. Does it also have anything to do with the time scales involved in the system?
One thing which I have not talked about is that unlike in the bicircular field, which is really long, like let's say hundreds of femtosecond, here the pulse duration is really short. So this is of the order of let's say tens of femtosecond. Okay. All the results are after switching up the laser. So once you switch up the laser, how much asymmetry it has been created. So the way the single cycle pulse create the asymmetry, it's like a kind of putting a quick force on the system. It exerts the force. So it means that the system also relaxes quickly. So the relaxation of your population after, because at the end of the day, everything's supposed to come back to the ground state. Okay. And before that, you need to perform the operations. So in the case of the single cycle pulse, the relaxation happens much faster than the bicircular, because bicircular is not created by the quick, but it's like slowly you are taking away your electron from isotropic to the anisotropic region. Okay. So to us, the omega to omega approach is much more robust when it will come, hopefully, for some technological application than this quick one. But quick one was the idea that how the asymmetry of your light is going to imprint on the asymmetry of your valley polarization.
Yeah, that's true. But what I was wondering is that, see, when the carrier envelope that you showed for one cycle versus, say, a couple of cycles or 3 cycles, there the envelope width is still the same. What is happening? Yes. The time period in which the field switches its direction, that is changing, right? So that's why I was wondering, is there anything, I mean, what is the typical decay times for these kind of excited states that have been generated?
Yeah, so this is very interesting question. So let's first talk about the things that we know from our conventional knowledge. So if we have atomic systems, typically the decay time is of the order of nanosecond. That is the, let's say, take something like that, right? Now, when we go to the solid, again, we can think of like a two-level system or upper and lower level system when you talk about the gap. And the decay time comes back again, something like, let's say, the nano to the picosecond systems, okay? And these are the direct recombinations, direct decay, you could say it. Unlike in these materials, graphene does not have this band opening. So this one. So what happened, what I call as an interband, so the relaxation is not happening by interband, but more like intraband. And intraband is always a slower process. So in graphene, the decay is much slower than equivalent materials like MOS2 or something like that. So they are going to be in picosecond or something like that. But there is one problem which we are working on, and we want to test it, that after some point, let's say 50 femtosecond or whatever number, we need to bother about the lattice motion or the nuclear motion, which is not involved here, which we not tested. So these are still, we are looking the pure electronic motions. How these lattice motions will affect the valley polarization is the next step that we need to bother about, which had not been addressed in any of the cases, whether you talk about the gapped material or in-gapped material, lattice motion has not been looked carefully. So this is the next task we are talking about. The other thing which is challenging to us, so we have created the polarization or asymmetry between the two valleys. Now the question is that whether these two valleys are anyhow related, is there any coherence got set up between the two valleys, and whether we can entangle these two. These are the two challenges that we want to solve in coming years or something like that.
So I actually don't see any more questions. So can I ask something?
Can I
Sorry.
ask one more question?
Yeah.
Sure. Go ahead.
Gopal, I have another question. See,
Yeah.
when we talk about this technology or this possibility of using it as qubit, and so see, I can understand that this k and k prime values together have giving this polarization is what, 1 qubit in principle.
Yes.
Right. So now, this is something which I was wondering, that if I want to now make several qubits, so of course you have to have the coherence among them. But isn't it the quality of each of these k and k prime values itself will depend on the size of the graphene, for example? So I mean, for example, if I want to think about a device out of this, I will have to make several laser points or several laser beams going at different spatial points. But moment I do that, shouldn't the quality of this k point also get affected by this limited size of each spot on the graphene?
I think that I cannot answer actually, but what I can answer is other thing that you have pointed out. So yes, you create, let's say the qubit so-called at different spot, but if you want to make sure that these qubits talk to each other, you need a homogeneity in your sample. Okay, and that's where the graphene is superior over the other materials because of the sample preparation or the quality or the cleanliness that the way you can prepare it. And that's why we thought that if you can see the let's say the valley polarization and all the qubits and all these things, that can hopefully motivate the experimentalists to look and take this field further. Okay, one thing is a kind of message that people don't take it that immediately tomorrow we are going to see something made of tronics and all these things. We all know that whatever today's so-called quantum computers are working based on ultra cold temperature or ion trap, this technology, this took almost 30 to 40 years, right? And many people have contributed significantly, and at least to my knowledge, 3 to 5 Nobel Prizes have been awarded to these technologies, not to particular one, but going from micro Kelvin to the nano Kelvin temperature, then achieving the boson condensation, and then realizing other all kind of things. So all these things requires some time to work it on, and the whole community effort goes. So hope is that within let's say 5 to 10 years on these things, people will start thinking about using different kind of lasers and playing with the graphene and seeing different kind of polarization, and then maybe people can come up with different kind of devices. We don't know, but hope is along that way.
Yeah, but that's quite correct actually, and it's very interesting that this is another possible candidate for realizing those kind of technologies or equipment. But what I've also wanted to know actually is that in your calculation you must be having certain lattice size, right? I mean, a certain size of the graphene that you are taking into account, or it is just a large sheet and size effect you are not taking, you are not bothered.
No, size effect is not taken into account because for solid it's only the unit cell matters. So that's what we have taken, the unit cell. Now we need to come up with another setup that we can create a large sheet, and then we start putting different focal spot and seeing how this connected. That is one way to go it, but what we thought, instead of going into this direction, we can talk about how the two valleys are correlated with each other and whether we have entanglement or not. There are several, let's say, the directions that opens up. But with the limited time, we can address only few questions and let other people join the community and start addressing other questions.
Very nice, Gopal. I enjoyed your talk. Thanks.
Okay, so maybe I can ask one question, which is I don't know. It might be a bit more to do with the experimental scheme, right? I mean, later on,
Yeah.
but something to what Weber was saying. So, for example, like each pair of these values can act as a qubit, right? Now, if we actually want to do kind of computation with it, one needs to, sort of selectively excite these, right?
Yeah.
So I mean, so what kind of a scheme one can have? Because I mean, making laser focal spots with a single laser is okay, but then how do you selectively excite some and not the others?
So at least the way I can think of, again, I'm with the disclaimer that I'm not experimentalist, but I can think of. So let's go back to the ion trap based. So you have a different ions and you can, let's say, trap 50, 80 ions, doesn't matter, but only at the time that you want to create a coherence or you form a qubit, only 6 to 8 ions are meaningful. That's what Blot and all these people started. Now I have not followed that field, but early that's what I remember. Going from 4 atoms, 4 ions to 10 ions to so on and so forth, right? So now what I could think of, and that I think addresses another question that Vaibhav asked. So let's see, I have this graphene sheet, and each hexagon can be treated as one unit or one ion equivalent, okay? And now I have a focal spot. So at one time, all the k values can be populated, not the k prime values. And because it's done with the same light, so all the k values will be coherently coupled. And then I can start tuning. So all these things which comes, because the focal spot, I believe it will be in the micrometer size. That is the typical size of your focal. Whereas the unit size of one graphene, one hexagon is something like 5 angstrom, 6 angstrom, and so on and so forth. Nothing, not more than that. It's just double the carbon-carbon distance. So right. If it is 1 point something, so the total will be 2 to 3 angstrom maximum. Okay. So within the micron size, you will have a large sheet of your graphene, and then each atoms are equivalent to the atom you can treat this thing. Because you think of, in real space, each atom or hexagon atoms are corresponding to each values. That is the mapping that we have real space to the momentum space. Mm-hmm. So I think that could be a possible way. Mm-hmm. Okay. I mean, this is one way right. of thinking. Yeah. But we are in touch with some people and trying to learn with the experimental point of view and see how far we can go it. But at least up to a theoretical level, this is still a fascinating topic. And to me, it's a new field. So I'm learning a lot, trying to do something in this direction. That's what we have.
Okay. Okay. So, Vaibhav, anything else you want to probe?
No, but I see I was actually wondering about the finite size of the laser beam itself, how much effect it is going to have on these, I mean, how much it is going to blur this K valley and K prime valley position just because of the finite size and the spatial distribution of the laser field. But then, as Gopal said, I mean, it's something which is one has to actually perform the experiment and see.
Right.
It may not be that trivial to look into.
But I'm not sure. I mean, I was checking some of the people here in our institute, and to my knowledge, at least I haven't found anybody who is doing or who have done any kind of value tronics or this thing. So I don't know whether anybody is in TFR from experimental point of view. Or I mean, I was thinking once to write to, for example, Mandar, to see what is his opinion and all these things, where he can say something, but I haven't written anything to him. Maybe I will try to contact him. But if you have anybody who can help us to understand more into this direction, at least where this field can go or what can be, it will be great.
Yeah, actually, Mandar is a very good person to look into, because it may not be just this. I mean, laser coupling is one way of looking at it, but I don't know. He might even have some idea about STM coupling. I mean, using STM addressing each K and K prime.
Right.
Yeah.
You can actually do something interesting over there as well. So Mandar is the correct person to write to. You should talk to him.
Yeah. I mean, he's in the campus, so it's easy to catch him. I don't need to travel to Kolaba. Yeah.
But then that's another thing which I was actually going to ask, is that instead of doing it with the photon field, if I now bring in STM tips and actually try to couple these K prime stuff with additional electron putting in, what kind of effect one can think of? But then while thinking itself, I thought it is too wild and too random for the time. So that's why I restrained myself from saying anything. Yeah.
I mean, to me, going from atomic system to the graphene itself is a long jump, and now I want to equilibrate at this point. And then STM is another new territory. Maybe after 10, 15 years, I will try.
Yeah, sure.
Yeah, but I will contact him. I will write him and see what is his opinion. Maybe he can come up with some another brilliant idea.
Okay. So if there are no more questions, then Dhananjay?
Vaibhav,
Yeah.
If you want to do this experiment, you have to deposit on the substrate, isn't it? This experiment, if you want to do with the laser, so this graphene has to, you can put on substrate some let's say gold, silver, or some single crystals.
No. So typically there are two ways people have done the experiment, at least to my knowledge. Either people can use freestanding graphene, which is possible because it's quite stable and homogeneous, or people use silicon carbide as a substrate. These are the two most common ways people have done it. And I think I forget to mention that there are two recent work, just 2-3 years back, that people have generated higher order harmonics from a single layer graphene. In one case, they have put into the silicon carbide. In another case, it's not evident that how they have done the experiment.
So then this substrate will affect when you use the laser, no? So it will, the substrate, that electron emissions from the substrate, it will come to the graphene, and that may affect this process, or?
That may affect, but at least what I have read from this one paper, that substrate only what it does, it just opens the gap a 0.1 MeV or 0.2 MeV of the graphene. Other than that, it doesn't do anything. At least, let's say people are able to wash out or subtract the signal coming out from the substrate. That's what I understand.
Okay, so if that is the case, then let me take this opportunity to thank Professor Dixit once again on behalf of the society for accepting our invitation and introducing this, I think, very exciting world of valleytronics to us. And yeah, I think this gives a lot of things to think about now.
Yeah.
Right?
Yeah.
So okay, so thanks a lot. Thank you.
Thank you very much.
And
thanks, Gopal.
And I would. Right. And I also thank the audience members for joining us in this colloquium. And there will be more activities from the society in future, and I will keep you posted about those. So thanks once again. Thank you.
Thank you. Thank you.
Thanks, Gopal. Very exciting work.
Thank you. Thank you. Bye.
Yeah.